Hi, my name is Muhammad Tariq, and this lecture is a continuation of last lecture. So, in last lecture, we discussed how we can relate or how we can make sets using different objects. And to represent those sets or to represent those relations, we used the approach, or you can say we used the technique of matrix. We can represent those relations using metrics. As in last lecture, we used the relation between people. We had the persons whose names were Jamie, Ali, Usman, Umar, and we showed the relation between them using the matrix. But the problem with that is if we have large number of people, 1,000 different elements or 2,000 or 5,000 different elements, so will this be efficient to represent the relation between them using metrics? So we discussed this problem that what if we have 1,000 elements, objects, or people? Will this be efficient in terms of time, space, and memory to create a matrix of 1,000 by 1,000, or 2,000 by 2,000, or 5,000 by 5,000? So the answer is very clear that this is not an efficient solution. So what is an efficient solution? Let's move towards that. Find and union, array-based approach. As an example, suppose we have the equivalence relation is defined over five elements. So here we have five elements. So these are five elements A1 to A5, and the equivalence relation is defined over them. So these are 25 pairs. So if we will make the pair, we will get 25 pairs, each of which is related or not 30 pairs. Okay, the 30 pairs is 5 is self pairs, which are, you can say, the reflexive pairs. So this is the information we have. We have this relation. A is related to 2, sorry, A1 is related to A2, A5 is related to A1, A4 is related to A2, and A3 is related to A4. So, or if we try to group them, we can represent these relations something like A1. Okay, we have this A1 and we have A2. So for example, let's say I have A2 here. This is one relation. Now A5 is also related to A1. So I can say, let's say A5 is related to A1. A4 is related to A2. This is A4, and A3 is related to A4. So then this is the relation we created. So as you can see, this is kind of giving a look of a tree. So now we haven't used the array approach. We used trees. So in trees you can say, or that we can maintain trees in terms of arrays. So if I can make the levels, for example, these levels I can make, and I can mark this is a zero index, this is 1, 2, 3, and 4, right? I can do like this also. So this is one of the approach of representation of the relationship between different elements or objects. So this is union find. What is union find? So what we did, this is union, right? So A1 A1 is related to A2. So this is actually a union, right? This is a union operation. So we unified or we grouped two elements which are related. So here we represented that group uh, in terms of an array, right? You can say it's like something like this. So we have uh, the root for A2 is A1. So we need to define a root also. So we represented this in this format, right? So we have union find operation. Find is actually searches for the element, and union is used to group the element, right? So union find operation keeps track of elements which are split into one or more disjoint sets. So as you remember, we with the Ahmad and Muhammad example, we had disjoint sets. The first example, if you remember, we had two persons. One was with the name Muhammad, right? and second was second was with the name Ahmed. So these were from different families. You remember we said these two guys are from different families, and so Muhammad is is in set one, right, and Ahmad is in set two. So these sets containing only single elements, right? And if we have any other relation between, like if we know any other person, then we can also add those in this set, right? So these are disjoint sets. This set is different and this set is different. So if we want to join them, so we will apply union, right? If we can say Muhammad and Ahmad, M for Muhammad, A for Ahmad, so we can make another set, right? And this is a new set, and we can call this set 3, right? So we have joined them using union. And how this works, I'll show you in detail, so don't worry about that. Now, how to perform union and find. To apply union and find, first construct a mapping between your objects and integers. I have some elements with me, and these elements are marked with some numbers. So you can call them different objects or different elements, whatever you want to call. These are some random alphabets, and I have represented each alphabet with a numerical number. So as you can see, this number, the arrangement of these numbers are equivalent to the arrangement of indexes. And I did this with intention. Why I did this, I'll explain you in the next slide. So here I have a note. Uh, this step is not necessary in general, but it will allow us to construct an array-based union find, which is very efficient and easy to work with. Now let's move towards its operations. So as you can see, I have numbers, I have elements, and I have their related numbers. And now these numbers are in an array, and these are the array indexes, right? These are the array indexes. So I have an array which contains the numbers, and the numbers are the same as of the indexes. Now, what I can do and how I can perform union operations on these numbers. So I have some instructions with me, right? I have some instructions, and the first instruction is C, comma D. So this means that C is related to D. Now we need to union these two objects. So I have C here, and the array index is 6, right? C is on 6 and D is on 5. So initially if I draw C and D, right? So initially they are pointing towards themselves, right? Because of reflexive property, right? As you remember, every element element is equal to or is related to itself, right? This is the first property of equivalence relation. So now I want to union this, so I'll have to make one element as a root and the second one as a child. So I'll make C as a root. Now what I want to do, I want to union C and D, and what I want to do is I want C to be the parent of D. So I can say C, and I have D here, and D will point towards C. C and D, they both are in same set, and C is representing the set, right? They are both are in same set, and C is actually representing this set, right? So now I have to make some changes in this array. So what I will do is, now I need to make changes in the array also. So now the C is a parent of D, so I can change this array. I can change the index number 4 to index number 6. So now we have the D parent is 6, and on 6 we have C. So the D parent is C. So now let's move to the next union, which is the next union is E and B. E and B. So we have E here and B is here. So I can say initially they are pointing to themselves, right? Initially they both are disjoint sets, right? They both are sets, but they are disjoint. They are not joined. Now with the union operation, we will join them and let's make B the parent of E. So it will be something like this. The B will be pointing towards, sorry, the E will be pointing towards B, and we don't have E anymore, right? And B is still pointing to himself. So this means that B is the parent of E. B is the root node. So now what I can do here, what I can do is I can mark E as 1. So at index 0, we have 1, and 1 is actually the parent. And on 1, when we go to the index number 1, we'll get B, right? And this is also a set, right? This is a set, and this is a set. So now let's move to the next element, which is A comma F. Now here we have A and here we have F. So now initially they are pointing towards themselves, A, and this is F, and they are disjoint sets and they are pointing towards themselves. Now let's make A as a parent and let's make F as a child. So we have this structure now, and we don't have A like this anymore, and F is pointing towards A. So what I will do is I will change the F and I will replace it with 2, because 2 is the index number of A, right? F is actually referring towards A, and A on index 2 we have A, and the index 2 and the value of the index and the value of that uh, that element is same. This means this element is not not a child of anyone, but this is the self reference. This is the reflexive reference or the reflexive element. Now let's move on and let's apply this union F and G. So now F is here. Now this is the interesting one. And where is G? G is nowhere. So G is here. Okay. So now F parent is A. Now if you go to the F, F is referring towards 2. So the F parent is A. So we will connect or we will join G with A, because this set, right? This set is actually represented by A, by the root. Okay. So now we will union G with A. So here is, let's say, G, and G is now referring to A. And we will now change this. We will change the data of index 7, and here we will write 2 because it's referring to A, right? Okay. So now we have completed this operation. Now let's go to this one, A comma C. A comma C. This is the next operation. Now let's check where is A. A is here, A is here, and C is here. Okay, so now we have two different sets. We have C here and we have A here. So there are two different sets and we need to join them, we need to unify them. So what we can do, we have two approaches. Either we add A towards C, or we add C to the A. So the better approach is add the small number of elements to the larger number of elements. So what I can do is, with what approach I will apply. Now I will add C to A. It means I will make this set as a child. I will make this whole set, right? I will make this whole set as a child for A. So for that, what I will do is, for that I will make a reference to this one. Okay, I will make a reference to A, and I will, for this I will just change only the index number C to 2, right? I've made the change, and now it's referring to, as you can see here, it's referring to 2. So as you can see, we did not do anything complex. We just only changed the reference, and now this set is now has been this set has been unified, has been grouped with A, and is actually a part of A. Now let's move further and B comma H. Now we'll have to unify B with H. So where is B? B is here. B is here, and H. Okay, H is a single element. H is a single set. So now here we have H, something like this, referring to itself. So we will unify this with B. So let's say we have H here, and H is now pointing to B. So we'll change the value of H, and we will place 1 here, because B is the the index number of B, or you can say the element of B, the data of B is 1. So you will replace 1. So now the next operation is D comma G. So where is D? D is here, and G is here. So as you can see, both of these elements are in the same set, right? So this is a set we have. We have this whole set, and both of these elements, G and D, are in the same set. So since they are in the same set, we need not to take any action. So when we will do find G, so when we will do find, right, we will do find operation. We will apply find operation, and we will say find G. So this will return us A, because A is the root node. And when we will apply find D, this will also return me A, right? So because since these both are same, so A is equals to A, right? So we need not to take any action, because both of these elements are in the same set. Now let's move to the next instruction, and the next instruction is B comma A. So let's see, here is B and here is A. So we have two different sets, we have two disjoint sets, and now we want to make, or we want to group them, we want to unify them. So as per the rule, we we add less the set which has less number of elements to the set which has greater, or the large number of elements. So we will add A, sorry, we will add B to A, right? So to do that, we will make B point to A, right? So, we will make B point to A, and now B is pointing to A, and we will change the reference of B here. We will change the reference of B towards A. So A is the only element whose index number in data is the same, and all other elements are pointing towards different elements. So as you can see, with this with union find operation, we unified the different disjoint sets, and we only need to take care of their element numbers, and it's a very efficient operation. And this is how we can efficiently manage, and we can unify different sets into one set. Now let's look at some definitions. To find which component a particular element belongs to, first find the root of that component by following the parent nodes until a self loop is reached. As you saw, so here as you can see, the so A here, A is having a self loop, right? A is having a reflexive property, because A is the parent now for all other elements, and all other elements are referring to the A. So initially I showed you when we had some disjoint sets, so those elements were pointing towards themselves. And as you can also, I also showed you here, all the elements were the same as the index numbers. Okay, the next point is find. To unify two elements, find which are the root nodes of each element. of each component, and if the root node are different, make one of the root node to be the parent of the node, right? Make one of the root node to be the parent of the other. The same here we did, as you can see. So we did the same here as we, for the B, as you can see, we referred B to the A. So in the same way, C is also referring to the root node of an element. The steps we followed, let's see some definitions of the steps. The input is initially a collection of n sets, each with one element. So we initially we had every element as a disjoint set, and every element was referring to itself. So we had n sets, and each one having only one element. The initial representation is that all relations except the reflexive relation are false. This was also true because all the elements were referring to themselves. All the elements were reflexive initially, right? Each set has a different element so that S intersection Si intersection Sj is equals to null. This makes the set disjoint. So every element was different. Every element was in his own set, right? So it was a intersection is actually null. Find returns the name of the set that contains a given element, that is Si equals find A. So I showed you that. So let's say, for example, so let's say I have an element, I have an A element, and this is a reflexive element, right? So if I say find find A, so it will give me A, right? And if I have something like this, if I have something like this, and now I will say find find B. So this operation now will give me A because B has a root which is A, right? And every element, which is every single element, for example, this is a single element, this is a single set having a single element. So initially, every single element, every single set will point to itself, right? And every element is single when it is disjoint. When it is, for example, this is B, this is D, whatever name you can give, they all are reflexive sets. They all are disjoint sets. Okay, union merges two sets to create a new set which is K, right? If we union them, so let's say if we union A, B, in that case, so in this case here we unioned A and B, and we got a new set which is A. Okay, if we want to add the relation A relation B, then we first see if A and B are already related. First, we need to check, are these already related? Then we would not perform any operation. Otherwise, we will union them. This is done by performing find on both A and B to check whether they are in the same set. Remember, we did for the operation for one of the operation in previous slide. If they are not, we apply union, which merges the two sets A and B belongs to. The algorithm to do this frequently known as union find for this reason. This is very straightforward. So here is the example. The union of D and G, they both were in same set. So when we performed find operation, both results were the same because both were referring to the same root node, which was A. Okay, when and where disjoint set is used, I'm showing some of the usage of disjoint set. Kruskal's minimum spanning tree, grid percolation, network connectivity, least common ancestor in tree, image processing, and maze generation. These are some of the uses where disjoint sets can be very handy. Okay, now let's do some analysis. A typical tree traversal is not required, so no need for pointers to children. Instead, we need pointer to parent. So here, when we unify different elements, so as you have noticed that the children were pointing towards parent. because we do not need a tree traversal as we did in binary tree or binary search trees, AVL trees. That kind of traversal is not needed in disjoint sets. Instead, the children here points toward their parents. Union is clearly a constant time operation. So, as you have seen, that when we do the union is a constant time operation. We only just change the location of array, and that's all. We merged two elements just only when we change the location of the element. Running time of find is proportional to the height of the tree containing node I. So because we have relation something in which we have parents, okay? So we have a relation something like this, that we have parent and child are pointing towards them. So the height of the tree matters, right? So to find, if I want to find something, so I'll have to traverse from bottom to up. Okay, this can be proportional to n in the worst case, but not always. Okay, so can we improve that? Can we improve this find operation to to quickly find the elements? And yes, we have a technique which is called path compression. How path compression works, we will see that in next lecture. So for this lecture, we have completed some of the major parts, or you can say major operations of disjoint set. We created disjoint sets, we applied union and find operations, and we also did a brief analysis of this data structure, that how efficient it works. I will see you next lecture. Thank you.